particles in 234 to make it almost a thermodynamic system. So it's like a white hole spitting out these neutrons with an energy of 1.28 MeV. This is known, but actually nobody put two and two together. Why? The reason is, okay, so here it's coming out like this, and it look like this if it came up, but we're not moderated. So that tends to drag it down to lower energies. This is the mean effect of the thorium, then the sodium comes in, and then it means something that's trying to thermalize. But it's not exactly thermal. This is stuff coming down from the top at high energy, trying to become thermalized. That's not a Maxwellian. It's a raised Maxwellian. Okay? On this side, it's not Gaussian, it's a power law. And that's why cosmic ray acceleration produces power laws. So that's, when I understood this, I said, Roger, I think I understand. He said, yes, that's right. Okay, so that's it. Okay? So this is what we call spectral energy distribution. I hope all of you know what spectral energy distribution is for a great reactor. Okay, once you have this, you can calculate everything else. You can calculate the critical mass. If you have U-233 in the core for this particular reactor, with a spherical diameter is 2.4 meters, it's 91 kilograms. And the breeding ratio is 1.16. If everything is clean, if there's some stuff that absorbs neutrons more than I've accounted for here, like fission product, this will blow it. You need one to replace the ones that you get. Okay. So the 0.16 is potentially available to expand your fleet of nuclear reactors. To get it started, you need plutonium, because plutonium has a very large cross section. You only need 26 kilograms of it, and the conversion ratio, you can think of it as well. What I'm basically doing is taking plutonium-239, which is a dirty fuel, and convert it into uranium-233. So what's the conversion ratio? The answer is about 0.6, but that's because I've ignored all that other stuff up there. If you take that into account, probably more like 0.8, 0.9. Why can't I specify more accurately? Because spent fuel is inhomogeneous like crazy. Depends which reactor produced it, how long it's been stored and decaying, and that's what makes reprocessing so difficult. Today, all right, when people want to do reprocessing in France or anywhere else, or in Japan, you take these different things, you mix them together, you fabricate a solid. If you haven't fabricated well, there's going to be a hot spot, and that's the first thing that's going to leak. So your weakest point, so it becomes very expensive. The molten salt reactor, I don't care. I get this from there, I get this from there. I pump it through pipes, it's turbulently mixed, it's homogeneous. Okay? That's why reprocessing is cheap with molten salt. And that's something Wigner recognized. Okay, so you need plutonium to make, so you can ask, is there enough like water reactor waste? I hate to tell you bad news, there's not quite enough. If you got it, you're in good shape. The United States is in good shape, got lots of waste. They think it's a big problem, it's a huge resource. Taiwan has huge amounts of waste, it's a resource, but we're not allowed to use this reactor. But other people will want it. If this reactor gets built, China will surely want Taiwan's reactor. You can send it there, or can send it to the United States. Many, many people will want so-called waste. It's not a waste, nothing in nature is waste. You just need to spend a little bit. So can you dissolve enough plutonium? Well, this you need data points. Again, it's a solubility question. Right? So these data points were done by a man named Charles Barton Sr. I didn't know this person. He's older than me and has passed away. But his son is a blogger, okay, Charles Barton Jr. And he runs a blog site called Nuclear Green. You can learn a lot about nuclear reactors. That's the beauty of this reactor. So many fans out there, they're doing a lot of the work that professionals should be doing. Anyway, so these are different mixtures of sodium fluoride, beryllium fluoride. This is the one that we want, Luker. They're plotted in a so-called Arrhenius diagram, where you plot it against the logarithm of the inverse temperature. And that's because activation energies go like e to the minus delta E over kT. Okay? So this guy won a Nobel Prize. There are lots of Nobel Prize winners in this subject, including those guys that invented black holes. Okay? So theory says it should plot on a straight line, and does plot on a straight line. So you can do extrapolations fairly safely. Everybody does it at relatively low temperature. We want it at high temperature. So if you extrapolate, you find you can dissolve a maximum concentration of 2.29%. You need only 0.569%. So that's not a problem. Okay, I think I won't go into why this is S process instead of R process, but this was a source of debate between Fermi and Wigner. All right? Wigner said basically we should build molten salt reactors, make the fuel elements liquid. Fermi championed the solid point of view. Fermi came up with a very good objection, which was basically whether this is S process or R process or partly R process. And Wigner, for once, didn't quite give the right answer, or at least it was a better answer. That answer prevented the adoption, in my view, of the championing of many people in the field of this reactor. You thought you had to extract the intermediate product out, you could extract it fast enough was a question. If you could extract it, you could make weapons out of it. So it became a mess. By adopting a pool, a large enough pool, you can avoid all that. And you now have to worry about it. I won't discuss why this is so. There's a formula. But anyway, so depends what power you run it at, whether S is large, and so you produce, compared to 1, and so you produce mostly U-233, or S is small, and you produce mostly U-234. Okay? So, depends what power you run it at. People don't realize you can run the nuclear reactor at any power you like. Okay? Fermi ran it at half a watt. Okay? So you get to choose. What do you like? Well, half a watt is not very useful, but it's good for demonstrating the principle. Okay? So, this thing has enough heat capacity and heat transfer power, so in principle you can run it at half a gigawatt thermal units. So this would run like power a city of 50,000 people, okay? You know, thing that's about this big. But it turns out that to not destroy the graphite, you only can run it at maybe 60 megawatts. And the reason for this is the following. This is something that Kandai explained to me. I always thought of graphite as kind of benzene rings without the hydrogen at the end. Then they're attached to hydrogen, but that means the bonds are completely different. Okay? In benzene, roughly speaking, simplistically speaking, each carbon has roughly 1.5 bonds. So that's strong, but not real strong. Things can get in there. But in graphite, there's only carbon, except at the edges. And that means it has on average 2 bonds. If I have 2 bonds, that's darn strong. It's very hard for anything to get in there and break. So graphite, by that principle, is not corroded. And that you can see from the picture we showed in the beginning of a piece of graphite in molten salt at 900C. You can see it's transparent, hopefully visible, and infrared. It's glowing red, okay? Basically the temperature of a brown dwarf. And after the reaction is done, this quartz test tube is a goner. This has been completely corroded. That graphite, nothing has happened. Completely because of this thing. So it's not corroded by molten salt, not corroded by fission product. It's the best material you can imagine. But it has a problem. It's a solid. It has bonds. These bonds can be broken. How? You come up with a fast neutron, let's say more than 50 keV, it creates a fast ion Now you've got ions rushing through the material, and you make holes. Now, at first, it's not bad, because you never have perfect graphite. Graphite doesn't always come stacked in planes like this, it comes sometimes like this. So there are holes, you would like to close those holes, and that's what it actually does. Okay? It first causes things to contract until a minimum size, and it causes it to expand again. If you have contracting things, it's good. If it was tight at room temperature, and you run it now, and it contracts, all the fittings become tighter, so you're not going to get leaks. But when it starts to expand, you can get leaks, especially if it expands beyond your original size. So that depends how much neutrons, flux, you've accumulated in time. That's called fluence, and you can calculate it. This affects all fuel elements, whether you make them out of graphite, whether you make them out of metal, they will suffer radiation damage from fast neutrons. So we can calculate, if you run it at 60 megawatts, and you clean the fission products by a factor of 4, what the lifetime is, and it's not that great, 13.9 years. But if you use fuel rods in a light water reactor, you have to change them 1.5 years, every 1.5 years. Okay? So it's roughly 10 times better than fabricating metal fuel rods. That's why we think this will be cheaper than light water reactors. And but now, if you take this stuff out, what are you going to do with it? You have a lot of graphite, you have some fission products embedded in it. You've got to reduce the volume, otherwise you have a lot of carbon to throw out. No problem. Carbon is burnable. You wouldn't like to burn it in open air, okay, but you can burn it inside molten salt. And we have this thing already. And sometimes burn, graphite ground up in the analog of this in test tubes. We've done it here, but not quite the graphite yet. It's called catalyst enhanced molten salt oxidizer. You turn all fluorides into oxides, that's much safer. Fluorides are dangerous to store for a long time, because if you have things bouncing around, you cut down, fluorine can get loose. Fluorine is corrosive like crazy, okay? But oxygen, if you turn it into oxide, you release oxygen, that's okay. Oh, it smells good. Okay? So you always want to turn nuclear waste into oxygen. And we already built this thing for our other projects. We know how to do reactions in it, so we think we can use it. Okay, let me skip this. This is another question of whether you have R or S process. And here, the final step is actually an R process. That same formula, S, is now 7.4 kilowatts over power, because this thing has long enough lifetime to capture a neutron. So if you run it over in megawatts range, S is very small. So it becomes R process. And indeed, any thorium-232 that you produce into making the thorium-231 ends up becoming U-232. So no problem with that. Okay, here's the so we can calculate the rate at which you make U-232 compared to U-233. It's just a ratio of 2 cross sections, and you're averaging over the distribution function. So it does depend on the distribution function. And the answer is 6 times 10 to the minus 4. And that, you can ask, if I work to try to build a bomb, critical mass is about 16 kilograms. It's not a top secret or anything. How long can I work at it at a distance of a meter before I'm dead? The answer is 1.5 hours. So, all right, comes in the next martyr. You're going to kill 1,000 of these guys before they get a bomb. That's pretty good. Better than anything else. So probably people are not going to use this. Even if they could, you can easily detect a 2.6 MeV photon. You can put it in a cargo container. Geiger counter, you know it's there. So this thing, proliferation is even if you don't know it's there, and they want to time things with any kind of electronics time, it's going to destroy it. So there's no way, hardly, that this thing can be used to build bombs. Let me end by just discussing two things. What is all this chemical cleaning? How hard is it? So suppose I want to clean the fuel salt. So I want to first extract the uranium from all the fission products and all the junk that's there. How do you do that? Well, it's in a molten salt, so if you add fluorine, F2, to it, you can turn UF4 into UF6. Uranium has two valency, either +4 or +6. +4 is a liquid, +6 it becomes a gas. It just bubbles out. You know, no hands. Just put in some fluorine, boom, bubbles out. Okay? Of course, you've got fluorine that attacks almost everything. One thing that doesn't attack is ceramics, like aluminum oxide. That's a very stable thing. So if you use an aluminum coated container, it should work. Okay? That's why people, when you centrifuge things to enrich uranium, the uranium F6, you will always remember people say they need to use aluminum tube for the centrifuge tube. I never understood that.